Today we're going to talk about impulse forcing. Let's take a look at a damped harmonic oscillator. So the second derivative of y plus 2 times the first derivative of y plus 26 times y is equal to 0. All right, this is our homogeneous equation. This is what happens when we're not driving with any sort of force. And then here on the right hand side, this is where we have been including some forces. Sometimes they've been periodic forces, sometimes they've been constant forces, sometimes they've been exponential forces. But actually, hitting this system with a force is not really the right way to think about this. What we've really been doing is hitting it with a force or applying a force through time. Right? And force through time is something called impulse in physics. So force acting through time is impulse. Now we know sometimes we exert a force over a long period of time, and sometimes we exert a force over a very short period of time. Thinking of, say, a baseball bat hitting a baseball. There's a lot of force acting, and it's acting in a very short amount of time. So we want to think about how to mathematically model a large amount of force happening at a small amount of time. So we want a large force happening at a small time. Now, one way we could do this is we could do this with a sort of limit. Let's think about a bunch of different forces here. Let's have the time of 4 be this reference time we're going to have here. And I could drive this oscillator with a function that looks like this. It's equal to, say, a quarter from 2 to 6. Right? So the force is going to be applied over a total of 4 seconds, and it is going to be equal to 1/4 newtons over that time. So the total force through time here would be the area underneath this rectangle, right? Which is 1, right? Because I said it was 1/4 high, and it is taking place over 4 seconds. Well, I could instead deliver a similar amount of impulse by driving for only 2 seconds, but with a force of 1/2. Right? So the idea here is the impulse delivered to the system in both of these two is the same. In the first driving that I did, I delivered my impulse over 4 seconds. Now I'm delivering that impulse over 2 seconds. And of course, I could instead deliver an impulse, an equal impulse over just 1 second, right? This would have a height here of, let's see, this is half as wide, so this is going to have a height of 1 over 1 second. So all of these have the same amount of force applied to them. And so there's no reason why we can't stop applying a harder amount of force, but over a shorter amount of time, right? That's what we're trying to deal with, a large force happening at a small time. Now, let's think about how to deal with this thing mathematically. This object that we're converging to, right, is just going to be a really skinny, really tall rectangle. And when we take limits, we want to let it get as skinny as possible and as tall as possible. And of course, as skinny as possible is 0, and as tall as possible is infinite, and that's not a function. Okay, so this thing that we're talking about is not a function. But it is something called a distribution. Let's call this first function here G1. That's the first squat rectangle that I drew. Let's call this G2. And let's call this top one here G3. And we can think of what G4 we're going to be. It's going to be twice as tall and half as wide. And G5 will be twice as tall as G4 and half as wide as G4. Right? If we think about those functions, let's think about what integrating one of the G's against a function f is going to be. Oops, we forgot our all-important dx. Well, what is happening here is that really we are averaging. If you carefully think about what this g is going to be doing, it's going to be giving you the average value of f of x over this interval. Right? Because g of 1 is 1/4 times this interval, so we're integrating f from 2 to 6, and we're taking a quarter. That's the average value of f. When we integrate over g2, we integrate f over 3 to 5, and then we multiply by half. Well, that's exactly the average value of f over that interval. And so we're averaging f over smaller and smaller intervals when we integrate by this function gn. And so the limit as n goes to infinity of integrating our function f against this function g is, well, that depends on something very important about f. If f is a continuous function, then this would be f exactly at 4. But if f is not a continuous function, then this limit may not necessarily exist. Okay? The reason why this is f at 4 is because we're just averaging over smaller and smaller intervals, and if f is continuous, then that's exactly what we get. So we are going to give this limit a name. We call this function delta 4 of t. This is going to be an impulse at time 4. And if we integrate delta 4 of t against a function f of t, which is continuous, we will get the value of f at 4. Okay. So this is a function called sometimes the Dirac distribution. It's not actually a function, it is a distribution. It is a distribution in the fact that we can integrate it against any continuous function. So we want to figure out, this is an impulse of a large amount of force over a short amount of time, and we want to figure out what the Laplace distribution of this is, because we're going to try to solve differential equations driven by this character here. So let's think about what the Laplace transform would be. The definition of the Laplace transform says we integrate from 0 to infinity of this thing, this distribution, not a function, times this function e to the minus st dt. Now we're integrating over t, so s is a constant, and now we say, oh, well, e to the minus st, this is a continuous function. And so this is going to be equal to whatever this continuous function is at a. So this is e to the minus sa. So that is the Laplace transform of this Dirac distribution. All right, so we are going to be looking at differential equations, second order differential equations, where we'll have an impulse force instead of a force being over a long period of time. We'll just have an instantaneous force acting on the system, which you can think of as a baseball bat hitting a baseball or a hammer hitting a spring, something like that. Okay, let's try to solve some problems based on this. Okay, so we're going to start with that equation I started with at the beginning of this video. D squared y over dt squared plus 2 dy over dt plus 26y is going to be equal to delta 4 of t. So here we are going to hit the system with a force at exactly time 4. Just an instantaneous force. And we're going to let the system be equal to 1 at time 0, and the initial velocity is going to be 0. So we're stretching this system to position 1 and letting go. And then 4 seconds later, the system gets smacked with a force of magnitude delta. So we want to solve this differential equation, so we're going to take the Laplace transform. And the left-hand side gives us s squared Laplace transform of y by using the property for the second derivative, minus s times y at 0, which is 1, so we get a minus s, and then minus y prime at 0, which is 0, so we get no term there. Now we have the term from the derivative, 2s Laplace transform of y, minus 2 times 1. This 2 gets distributed across s Laplace transform of y minus y at 0. And finally, 26 Laplace transform of y equals Laplace transform of this impulse, which, as we just showed, was e to the minus 4s. Great. Okay, now let's see what we got here. On the left-hand side, we have, let's see how many L's. We have s squared plus 2s plus 26 L's. So we have that many Laplace transforms of y. And we have a minus 2 and a minus s, so let's move those to the other side. S plus 2 plus e to the minus 4s. Now we know what to do. We divide both sides by s squared plus 2s plus 26. So it gives us an s plus 2 divided by s squared plus 2s plus 26 plus e to the minus 4s divided by s squared plus 2s plus 26. Okay, so now we have to figure out how to deal with this situation. What we want to do is we need to kind of complete the square in the denominator to see what the situation is going to be. So completing the square in the denominator, this is corresponding to an s plus 1 squared. When we do that, we have a plus 1, so to compensate for that, the 26 is going to go down to a 25. We'll keep that on this term here. All right, so now what we need to do is we need to look at this first one. This looks trigonometric, so we're going to break it into two terms. One's going to correspond to a cosine, one's going to correspond to a sine. And then over here, we're going to do a similar thing. So here we go. All right, so we had the Laplace transform of y is equal to, okay, so I want to have an s plus 1. We had s plus 2, right? So I'm going to have an s plus 1. Now, I have 1 left over because I had s plus 2. But 1 is not going to look good here for figuring out what's happening with a cosine or a sine. Here, we don't want a 1, we want a 5 because we have a 25 in the denominator. So I'm going to put a 1/5 here. And I'm going to do the same thing to the last term. So e to the minus 4s over 5. And then we're going to have 5 over s plus 1 squared plus 25. All right, so now we're ready to take our inverse Laplace transform. Okay, this plus 1, if you recall when we discussed this before, this leads to an e to the minus t term. This is e to the minus t cosine 5t. All right, this plus 1 is another e to the minus t, so we get e to the minus t divided by 5 because of the 1/5, and this is going to be sine 5t. And then the last term is a time shift term that we might recognize. So this is going to be 1/5 u4 of t, because we have the e to the minus 4s. We have an e to the minus t minus 4 because we have this s plus 1 down here, and then sine of 5t minus 4. All right, so there's our solution. And what's happening here is we have, right here, this is what would happen to the system if there was no impulse. Right? This would just be what happened if we let the system have a starting point of 1 and letting the system just work out. This is the term that comes from the impulse. And we'll see, note that at time 4, the sine is equal to 0. So this is equal to 0. So at time 4, this part is 0, and it just slowly adds to this y of t. And if we looked at a picture of it, it might look like something like this. And then we get, right, because this is a decaying exponential. So we have a decaying exponential times a sine and cosine, so we have this periodic thing. But then at a certain point, this thing is going to be added in, and it's going to be much larger because its exponential just got started decaying, whereas this one was decaying for a while. So we're going to have a sudden shift upward, and it's going to be continuous here. However, the derivative is actually a discontinuous function. Y prime is discontinuous because y prime here, this is going to be very close to 0, but then the derivative of this one is going to have a cosine, and at time 4, it's going to be equal to something like 1/5, plus or minus 1/5. And so there is going to be this abrupt jump in the velocity that'll be discontinuous, not the function y itself. Okay, that was an example with impulse force.